In this next subsection, I want to introduce suffix trees. These will be the star data structure of this unit that seem to magically solve a lot of interesting problems. They first solve the text indexing problem, but we'll see they are also applicable to many other problems on strings. And they turn out to be versatile and really a threshold concept. Once you understood suffix trees, suddenly you can solve more complicated problems efficiently. And they all start with these simple tries that we just defined. So let's see how this works here. A magic data structure. Before I want to show you how suffix trees work or what they are really, I want to motivate a little bit how formidable problems they can solve by looking at this specific problem. It's the longest common substring problem. It's an intuitive question. Maybe it's not the most immediate that you would come up with, but it does arise in applications. So you're given a list of strings. These can be of different lengths, and well, they are over a common alphabet, say, but otherwise we don't have any restrictions. So here's an example. And the goal is to find the longest substring that occurs in all of these strings. So in the example here, we only have two. And because the second is fairly short, you can check that alive occurs here and here. And if you spend some more time on this example, you will see that this is indeed also the longest or a longest repeated common substring. In general, there could be several of the same length, and then we can return any of these. So this is a simple to state problem, but imagine you're given these strings. How would you approach this? How would you find this this longest common substring? You definitely need time to read all the strings. That's no doubt about that. And it turns out you can actually solve this problem in asymptotically the same time, only a constant factor more. But how on earth would that work? Because it seems like you have to check all possible substrings, and even then, all possible substrings of one string, you would have to go through all the other strings and see if they occur somewhere. You could use something like our string matching algorithms, so you get that part efficiently. But going through all possible substrings, that's already quadratic in the size of the shortest string, and you would have to search through all the others. So it's quite unclear how to do this efficiently, and clearly not easy to do in this optimal linear time, the same time as you need to read all the texts, all the strings once. And indeed, suffix trees solve this. So let me show this in big. So suffix trees allow you to do exactly that. We'll see that you can construct them in linear time for this specific problem. We'll come back to that later today. And they allow you to do exactly that, even though it seems not possible at first. And to give more weight to this claim, here's a quote from a book. Dan Gusfield has written this book, which is essentially the Bible on suffix trees. It's the most comprehensive book of applications of suffix trees. And he says, although the longest common substring problem looks trivial now, given our knowledge of suffix trees, Don Knuth, famously known as the inventor of LaTeX, but also the author of the influential book series, The Art of Computer Programming, in a sense, one of the fathers of theoretical computer science and the analysis of algorithms, and a very clever person, called a genius by many, etc. So in 1970, he conjectured that a linear time algorithm for this problem, longest common substring, would not be possible. He didn't see a way, and he thought there is no way. And yet he was proven wrong. Now this happens occasionally. Even very clever people sometimes don't see a clever solution, and then someone else comes up with it. That's what happens in science all the time, or occasionally and repeatedly, maybe not all the time. But it's still remarkable because he was right with many other conjectures. So this is interesting, and it also maybe motivates you a bit more to learn about what this magic data structure really is. And here it is. This is the definition of suffix trees. It's not very complicated if you read it like this. A suffix tree, I use this calligraphic T to denote the tree, just to make it distinguishable from the text, the normal T. The suffix tree for a text is the compact trie of all the suffixes of T. And we append this $sign again so that all the suffixes are prefix-free, that no suffix of T is a prefix of another suffix. So we will always assume that this nth character of T is set to $, and the $sign again is some symbol that is not in our alphabet, an artificial end of file character if you want. Nice and simple, right? Very easy in a sense to define. And maybe at this point, let us look at a quick example of how this might be constructed. This was also a little bit of a recap about tries again. So let me do a smaller example. This might already take some time, but let's do banana and see how far we get. So this is our string. Now we take all the suffixes. So that's banana, and that's anana, and it's nana, and anna, and na, and $. And you correct me if I'm making mistakes. Okay, there were some questions that I overlooked. Sorry for that. Maybe I'll come back to these after this example. If I make any stupid mistakes during this construction, you will help me out and point it out to me, right? I count on you. Okay, these are all the suffixes of the text. And now we insert them into a compact trie. Now it's a bit tricky to do the compact trie in one shot, so at least for the manual construction, let's do first the standard trie, and then we create the trie afterwards. Okay. So we start with the root, and let's do the longest one first. So this is banana. So I'd have a B, then I have an A, banana, and the $. And here I'll just put 0 for the start index. This starts at 0, this at 1, at 2, at 3, at 4, at 5, and at 6. And that's 0, 1, 2, 3, 4, 5, 6. That's all. These are the suffixes of banana. So we've inserted the first one. Now we have to insert the second one, anana. Okay, it starts with an A, so we branch off in the root. And then, let's see, I'm trying to think a little bit ahead of myself. So let's branch out here. Do we ever have something else after an A, then an N? Well, at least the $. At the end. So let's keep it like that. And nah, this makes for a great recording. And the $sign. And that brings us to, well, the suffix starting at 1. Okay, and I guess you see the picture now, roughly how this goes. And we need another edge here for nana. Na. And the $. And that brings us to the suffix starting at 2. A few more left. Anna. it actually goes A, N, A, and then branches off with the dollar. So that was not too much work. We didn't have to create other nodes. And the same for NA, NA. We branch off with the dollar here and put in the 4. And $A is similar. We branch off here, A, and then the dollar is starting at 5. And just the dollar, we put that down here, that starts at 6. Okay? That is the standard trie. Now we want the compact trie. So we take this standard trie and do the compaction construction from last time. Let's move this slightly over here and make it a little smaller so I can fit this next to me. The contraction is now okay, I should leave room. We start with 0 here, and then the A, B, and dollar, they stay because these are leading to nodes. Sorry, the A and the dollar stay because these are leading to nodes that don't have exactly one child. Okay, and then this leads to a node with 1. The dollar leads immediately to a leaf with 6. Here the banana is actually contracted into a single edge and leads immediately to the leaf. Okay, so this here we got rid of a lot of nodes. And in the last case, we branch off to a node that now looks at the second letter. It starts with an N. We get rid of the A here. Okay. So let's go to this node A. That's this one. Now there's 2 branches. The one with the dollar is leading immediately to a leaf, so that's one thing that's easy. The other one again leads to a branching node here, and so that looks at the third character then, the character at position 3, and starts with an N. From that we branch off with a dollar to the suffix starting at position 3. And in the other direction, we have an N, and that leads us immediately to another leaf. Okay? So you see how these are connected and how we get many fewer nodes in this case. We're left with this node over here. And that one is... You don't see my mouse anymore, right? That one here has the NA. So that has a child with the dollar that leads to leaf 4. And it has another child also leading to a leaf. That's this. Okay? And if you want, you can draw the connection between the corresponding nodes. So this is the root. This corresponds to that one. This corresponds to that one. And I'm not doing all of them, just the internal ones. So you can see how these correspond to each other. I just wanted to give a very slow example again of how tries work, because many people haven't seen tries before. There were a few questions that I wanted to address. Let's do the easy one first. The comments on the class test. I suppose this refers to comments that you give on the evaluation. I'm not sure if I get flagged when these are added, so I can try to look over them. If you meant something else, maybe you have to clarify. The other question was, I suppose, when we had the earlier example for the tries. So let me go back a little bit on the slides to the try example. So the question was, if we search for AA, do we in the first step have to compare the first character with both A and B, or do we go to A right away? If we search for AA in this try, well, if this was not the example you're referring to, Franco, let me know. if we go a dollar, in either of the tries, we have to follow the edges down. I see. The question might be, do we have to compare all these characters, or do we just jump in the right direction? That's a detail that depends a bit on how you represent tries, but we will usually assume that you implement the children of a trie with an array, and the array is indexed by the letters. So you can, in one step, jump to exactly the right child in constant time, or find out that this child pointer is null and there is no such child. I hope this was the question you had in mind here. So this is about how to represent tries internally in a computer. And there's basically two options. You can either have, as I said, an array indexed by the alphabet. Then you hopefully have a not too big alphabet to do that. The other option is to store another dictionary in each node that maps alphabet characters to a child link. That's also possible. You could do a binary search tree inside each little node, but you would have an additional running time factor, log of the number of children then, so log sigma in the worst case. So people usually think of tries as having a way to go to the children in constant time, looking only at one character, not comparing the characters one by one. But that's an important point, yeah. Thanks for the question. All right, back to the other try we were looking at. This one. I hope I didn't goof in the example, but you see, what I want to get across at this stage is suffix trees are not by themselves magic. The definition is very simple. Just build a trie of all the suffixes. We do obsess about it being a compact trie, but other than that, there's no magic at this stage. And here's a slightly bigger example. Okay, it doesn't work. My favorite string that you will see many times in this unit is banana ban, because it has lots of self-similarity. If you take all the suffixes of that string and build the same type of trie, you get this picture, just drawn sideways so that it nicely fits on the slide. This is the compact trie in the standard way we draw it, except that here I cheated a bit and put the long labels on the edges. We don't really have that. And the first thing is we don't have to store all the strings in the leaves again, because we know there are suffixes of one fixed string. So we store that fixed string instead and a starting index. And of course, this is not how we represent it in the computer. I mentioned this before. The compact trie is actually storing just the first letter of all the edge labels, and then stores what is the next index that is compared. So this is again what we think of is often this. This is what you should have in mind when you try to work with suffix trees. But if you program them, what you really do is this, the compact trie as we've seen it before, and the leaves only store the starting index of the suffix. How can we construct a suffix tree? And this is where the magic starts. We can do something like what I've just shown you on an example. We insert all the suffixes one by one in a trie. That works, but it takes quadratic time, because you have to follow the search path for each suffix. So it's essentially inserting one of length n, one of length n minus 1, one of length n minus 2, all the way down to 1. But half of them are at least n half, so those already give you a n squared over 4 of total time. In quadratic time, you can do a lot of string problems already. Some are not even obvious how to do in quadratic time, but many are. this is not interesting. If your string is the whole human genome, you cannot afford quadratic time. It's just not, it just won't finish. So the suffix tree by itself, the definition is very simple and not magic at all. But the straightforward way to construct it doesn't help. Then it's not really useful. The amazing result that people found is you can actually construct the suffix tree in linear time, the same time asymptotically, only a constant factor difference, than just reading the text once. That's, in essence, the time you need to construct this complicated tree. The algorithms are a bit tricky. They date back to shortly after Knuth made this conjecture, I think, in the 70s. They were improved successively. They started out to be very complicated. They were certainly a theoretical breakthrough, but they also by now have heavy influence in practice. And towards the end of this module, of this unit, I will actually show you a way how to do this, how to construct suffix trees in linear time. And by now, the algorithms have become much cleaner so that they're actually definitely understandable. But they build on several steps, and we'll have to work our way through there before we finally get to this result. What we'll do for now is we just take the linear time construction granted, and first ask the question, let's suppose we have this magic box. So suppose there is a way to get this treat this as a black box, and there is a way to construct suffix trees in linear time. What can we do with this?